So what we have on the itinerary for today is to start our discussion on energy storage elements that are commonly used in electrical circuits. So the one that we're going to be talking about today is the inductor. So before we talk about what role inductors play in circuits, let's get a little bit of background information about what they are. Okay, so I'm going to draw a couple of shapes here. It's not particularly important that you guys know these or anything, but it's going to kind of lead us into some things. So the first thing that I'm going to do is I'm going to draw a cylindrical shape here. So imagine this cylinder as kind of a mandrel around which we are going to wrap a wire. So we wrap a wire around this cylindrical core many, many times, like so. We will have what is called a solenoidal inductor. I'm going to say that this coil here has N turns. So the number of turns that we wrap the wire around our mandrel makes a difference with regards to the inductance. And I'm going to attempt to draw another shape here, and I'm going to pre-apologize for how bad my drawing skills are. What I'm trying to draw here is a toroid or a donut shape. This toroid could have either a circular or rectangular cross section. It doesn't particularly matter. Both of these things are what are called core materials. And I'm going to attempt to draw a coil around the shape as well. Like so. And let's say, sorry, this is what's an example of a toroidal inductor. So let's say that these inductors are part of a larger circuit such that some amount of current I of t is flowing into this top terminal. I'll do the same thing here. For those of you that have had Physics 202, you know that anytime that we have a current, we have a magnetic field. And so when we wrap the wire around a form like this, what we wind up doing is we concentrate the magnetic field internal to this structure. So in this case, we're going to have field lines wrapping around the toroid like so. And this concentration of magnetic field is the energy storage behavior of our inductors. Now, if the current is time varying, what we'll see is that we will electromagnetically induce a voltage across the terminals of the inductor, or I'm going to call that voltage V of t, like so, positive polarity on top, negative polarity on bottom. The relationship between the current and voltage in an inductor is very, very different than what we have seen in a resistor, right? So in an inductor, the voltage V of t is equal to L, the value of the inductance, and we'll talk about that in a moment, times the derivative of the current with respect to time. Okay. This is going to be equation 1, and we're going to talk about this here in a moment, but I want to explore this concept of inductance here really quickly. Okay. So L is the symbol for inductance, where inductance is measured in volt seconds per amperes, more commonly known as the Henry. So inductance is a measure of how an element responds to a changing magnetic field. And this quantity L depends on a few different things. Okay. It depends on the geometry. So typically speaking, coils have much larger inductance than straight sections of wire because they concentrate the field, and so they experience the change in a larger scale. The material that's inside the coil also tends to have some effect on the inductance. Generally speaking, inductors are wound on ferromagnetic cores. So it's a material that is very easily magnetized because that internal magnetization tends to enhance the externally generated magnetic field, giving you a larger amount of what's called magnetic flux. And that larger amount of magnetic flux corresponds to a larger inductance value as well. All of those things are outside of the scope of this class in particular, but you may have heard about them when you were dealing with your Physics 202 class or other related classes. Okay. So we have this first relationship here. And this is a pretty important one because it really tells us two important things about how inductors behave. So let's say that I have a very simple circuit. So let's say that I have a current source connected to an inductor. And the schematic symbol for the inductor I've drawn here on the right-hand side is simply a coil. It looks similar to a spring, which inductances and springs are analogous to each other in mechanical and electrical systems. So let's say that we have some inductance here, L, and for the sake of argument, let's make it 1 Henry. And we have some current flowing through our inductor, and our goal is to determine what the voltage drop across our inductor is going to do. Okay, so I'm going to give us a couple of different waveforms that we're going to look at here. So the first one that we're going to look at is what happens if the current flowing through the inductor is constant. So let's say that my inductor current has some fixed value. For the sake of argument, let's call it 5 amps. What would we expect the inductor voltage to be?
A constant 5?
I'm sorry, what was that?
Just a constant 5?
So, if we look at our relationship here, we have a derivative-based relationship, right? So if I is a constant 5 amps, then what is the derivative of I with respect to time?
0.
0.
0. So if the di by dt part is 0, it doesn't matter what value L has, the voltage drop across the capacitor, excuse me, the inductor is going to be 0. Okay. So this means that in a DC circuit, inductors behave like short circuits. Okay. So anytime we have a DC circuit containing some inductance, we can simply replace that inductor with a wire and we lose no information whatsoever about the behavior of the circuit, okay? Because we can see from our mathematical relationship that if the current does not change, the voltage drop across the inductor will always be 0. So now we're going to look at a couple of other different wave shapes here, okay? We're going to be working towards the opposite end of the spectrum. So instead of no change whatsoever, we're going to be working towards a large change in a very, very small amount of time. So let's start with something more reasonable. Make my plot for my voltage here. So let's say that our current starts at 0, and then it takes 1 second for us to get up to 5 amps. Then our current stays constant for 2 seconds before ramping down and reaching 0. At t is equal to 4 seconds. So we know from our previous work that between 1 and 3, because our current is constant, our voltage is going to be 0. But what's going to happen over that interval from 0 to 1 second?
Would it be equal to the slope?
Right, so the slope times L, which in this case, L is just 1. So what's the slope?
1/5.
-5.
So it'll be +5. Just to remind you guys of how
5
slope
minus 0. Yeah, my bad.
it is going to be I at T2 minus I at T1 over T2 minus T1 under the caveat that T2 is greater than T1. So T2 represents a later point in time, right? So 5 minus 0 over 1 is 5 amps per second. Multiply that by 1 Henry, and we wind up getting 5 volts. When our current becomes constant, we will abruptly shift down to 0. What about when our current is decreasing from 5 amps to 0 amps? What should we expect to see?
Would it now be -5?
Exactly right. So now, because our slope is negative, we get a negative voltage until we hit 0 and stay constant, and then our voltage is once again constant. Okay. So what would happen if instead of it taking 1 second, it took half a second to go from 0 amps to 5 amps?
Be 10.
Right. So in half the time interval, the voltage would double. If we keep this trend up, what do you think would happen under the following circumstance? So let's say that this is my current. This graph over here is going to be for my voltage. So what if I allowed my current to instantaneously change from 0 amps up to 5 amps and then instantaneously change back down to 0, right? So the same time intervals here, 0, 1, 3, etc. This is 5 amps. What's going to happen to my voltage?
Would it be infinity?
Yes. So we would have an impulse here and a negative impulse here, and it would be 0 for all other points in time. Now, do you think there's a problem with that?
Probably.
You're 100% right. And there's very much a problem with it, right? So recall that voltage represents the amount of work done moving charge from one point in a circuit to another point in a circuit. So voltage is always dealing with some form of energy transfer. If the voltage is infinitely large for any amount of time, it means that we are transferring an infinite amount of energy, which, as we all hopefully know, is wildly impossible, right? So what that means is that the current, sorry, flowing through an inductor cannot change abruptly. I'm going to write this in a little bit of mathematical speak here. The current at any given point of time approaching from the left must be the same as the current approaching at that same point of time approaching from the right. Okay. So the current flowing through an inductor cannot change abruptly. All that really means is that it takes time for the current flowing through the inductor to change, right? It can be a very small amount of time on the order of nanoseconds or even picoseconds if we have a small enough inductor. But it cannot change instantaneously from one value to the next. Okay. And this is something that we are going to use to figure out how inductors behave in circuits that are undergoing a change called a transient condition when we have class after the 4th of July break. Okay, so we're going to put a pin in this relationship here, but this one I'm going to put a circle around it, is a very, very important thing to keep in mind when you're analyzing inductor problems where the system undergoes some abrupt change. And that abrupt change could be something as simple as turning the power off. How many of you guys have ever tried to unplug, let's say like maybe a hair dryer or a blender or a mixer or something like that while it was on?
I have to admit, I've never tried that.
Well, it's a terrible idea
Yeah,
unless you're trying to potentially set your house on fire, because what's going to happen is you're going to see arcing, okay? So you're going to effectively create a whole bunch of sparks that could potentially burn your house down. The reason why those sparks are being created is because when you change the amount of current flowing through your device by rapidly unplugging it or something like that from the wall, if that device uses a relatively large inductance, it's going to generate a voltage across its terminals so large that it's going to literally ionize the air. So it's going to break down the air, separate it into ions, which is going to cause sparking, which can literally burn your house down. So generally speaking, it's a good idea to turn your device off, which it actually takes time for the switch to engage and all of that kind of stuff, and let it settle down before you unplug things, because you could legitimately burn your house down. An interesting thing here, because this is a little bit of a tangent, but most mechanical switches actually have springs and stuff like that in them to cause them to open very rapidly to help clear that fault inside of the device so that you don't get sparks elsewhere that could be damaging. So like switches and stuff are designed specifically to be able to withstand that huge induced voltage that's trying to keep that current flowing for some small amount of time before it can settle to a value. So anyway, all right, so scrolling up here so we can look at this first relationship again. We've talked about the consequences of this relationship and how they tell us or inform us about how inductors behave. What we're going to do now is simply rearrange this relationship to get our second relationship, right? So this first relationship tells us what the voltage is when we know how the current is behaving. So if we mathematically rearrange this relationship, what we'll find is that the current flowing through an inductor can be expressed as 1 over L times the integral from -infinity to t, a current point in time, of the voltage drop across the inductor with respect to time. where I'm using these dummy variables, or this dummy variable t prime. So this just simply represents time, but because I have this t in my limits of integration, I shouldn't also have it down here, or it could be mathematically confusing. Okay. I've used this notation before, I just wanted to clarify it. Now, the only quote unquote problem with this relationship is that it requires us to integrate from negative infinity, which may not always be convenient. So instead, we could also write this relationship as 1 over L times the integral from T naught to T, where T naught just represents some point in time where the inductor current is a known quantity. We're going to have V of T prime, dt prime, and now we're going to add a term IL at T naught here. So this is our second relationship. Put a box around this. And this part right here is known as an initial condition. Okay. So what this means is that in a very simplistic sense, an inductor has memory. And what I mean by that is that present values of inductor current depend on how much current was flowing through the inductor in the past. So let's look at this really quickly with a simple mathematical example. Let's say that the voltage drop across an inductor is given by 5e to the minus 20t volts. And let's say that I of 0 was 1 amp. And our goal is to find the amount of current flowing through our inductor at 2 seconds. Let me just draw a simplistic circuit here so we can figure out exactly what's going on. So here's V of t. Here is our inductor. Let's make this inductor 50 millihenries for this problem. And we are trying to figure out what's going on with our inductor current at some specific point in time. So this is really just simple application of the equation that I just gave you guys, but there are a couple of things that kind of get a little weird sometimes. So I want to work a numerical example here with you. So our current I of t in general is going to be 1 over L times the integral from T naught T of our voltage plus the initial condition on our inductor current. So 1 over L is going to be 1 over 50. Since we're in millihenries, I'm going to get rid of the milli by putting a 10 to the minus 3 here. And we can recall that a henry is a volt second per amp. So the inverse of a henry is going to be an amp per volt second. So this is my 1 over L term. Now I'm going to integrate. So what is our T naught in this case? Anybody have any thoughts?
What, 1 amp?
So T naught is a time where the current was a known quantity. So this statement right here says that at T is equal to 0, we knew that the current was 1 amp. So T naught must be 0 because it's representing a time, okay?
Okay.
So we have 0 here. So we're going to integrate from 0 seconds to 2 seconds of this 5e to the minus 20t volts. T prime, dt prime. And now out here, we're going to add our initial condition, which is what that 1 amp represents, okay? So this adding 1 amp is happening outside of our integration. And when we do our dimensional analysis here, looking at the units and stuff, we'll see exactly why it has to be that way here in a moment. All right, so I have my 50 times 10 to the minus 3 volt seconds here. 1 amp on top, so that's 1 over L. I'm going to pull the 5 volts out. And we can see right now that this volt cancels this volt. So now we have amps per second. How do I integrate an exponential function?
Move the 20 down divided by, so it'd be 1 over negative 20 times e to the negative 20t.
Yes, so I'm going to write this down because you guys are going to be doing this a whole heck of a lot here over the next several weeks. The derivative of e to the alpha t is alpha e to the alpha t, and the integral of e to the alpha t is 1 over alpha e to the alpha t plus c, but I'm not a mathematician. So in this case, alpha is negative 20, so I'm going to pull that down. So 1 over negative 20. What do you think the units of this alpha quantity are? This is kind of a trick-ish question, just to be clear.
Unitless?
So it's not going to be unitless, but I can understand why you would think that would be the case. The exponential function e only acts on unitless quantities. Well, if time is measured in seconds and 20 is multiplied by time, then this alpha has to be measured in per second in order to make the units work out correctly. And what's going to happen there is that this per second gets multiplied by this second, and we're only left with amps as a unit, which is exactly what we should expect since we're trying to find a current here. So our last part here, at least for the integration, we are going to have e to the negative 20 t prime evaluated at 0 and 2 seconds. And all of this is going to be plus 1 amp. So I'm going to take my calculator now, and I'm going to clean up a couple of things here, right? So I have a 5 in my numerator. I have a 50 times 10 to the minus 3 in my denominator. I also have a negative 20 in my denominator. So all of this bit right here winds up looking like -5 amps. This is being multiplied by e to the minus 20 times 2 would be e to the minus 40. Minus e to the 0, which is just 1, plus 1 amp. And so let me throw that in my calculator. So e to the minus 40 is going to be a really small number. I wind up getting 6 amps because e to the minus 40 is so small that it's effectively 0. All right, so before we move along, any questions about the numerical example that we worked here?
Will for examples we're about to cover continue like this? Like, will we see this again?
For sure, absolutely.
I guess my question is, will we get more practice with that? And so, yeah, it sounds like yes.
Yes, so you'll have homework problems related to this. You'll have in-class assignment problems related to this as well. We're about to develop 2 more relationships, and you're going to be using all 4 of these relationships for inductors extensively over the next several class periods. Okay. There are all, just to give you guys a little bit of a heads up, there are also 4 relationships that we are going to develop when we look at capacitors next Monday. I am going to effectively do a little bit of review for this inductor material on Monday because I want to show you guys how similar these relationships are. In fact, I would argue they're not similar. They're literally the exact same relationships, except that we swap voltage and current. Other than that, the relationships are literally identical. So we'll see that on Monday. Okay, so let me scroll back up here and let's recap what we've talked about thus far. So we have an equation that gives us voltage when we know current. Now we have an equation that gives us current when we know voltage. So the next quantity that I want to look at is power. So the power absorbed by an inductor is hopefully very unsurprisingly simply going to be the product of the voltage across the inductor and the current flowing through the inductor. We can rewrite this equation though as L I times di by dt, since L times di by dt is simply the voltage. So effectively, in order for us to know how much current is flowing, or excuse me, to know the power absorbed by an inductor, really the only thing that we need to know is how the current is behaving, and from that we can determine everything. That being said, the overwhelming majority of the time, I personally usually wind up using the simple I times V relationship. That box we've been doing. So this is our 3rd relationship. And our 4th relationship is for the amount of energy stored in an inductor. Because I left my notes in my office at work and I haven't been there in a couple of days, I'm not super comfortable deriving this. So I might just derive this equivalent relationship for capacitors on Monday instead and just give you guys this one. The energy stored by an inductor will by definition be the integral of the power absorbed by the inductor. And this is going to come out to be 1/2 L times our inductor current squared. So since power can be expressed only in terms of current, it should make sense that energy can also be expressed only in terms of current. And so this equation also tells us that effectively, anytime there is current flowing through an inductor, there is some amount of energy being stored. As soon as that current stops flowing, or as soon as the inductor current reaches zero, all of the energy that was stored in the inductor must have been transferred elsewhere. Okay. And we'll talk about that concept a bit more next week, once again, when we get into the transient analysis problems. Okay. So these are our 4 relationships that govern the behaviors of inductors. We've talked about voltage as a function of current, current as a function of voltage, power, and energy. So the last thing that I want to talk about here today is how do we combine inductances? So we may see circuits that contain multiple inductors. So we need to go over the rules. Okay. So let's start by looking at inductors in series. So let's say that I have a portion of a circuit that contains multiple inductors. This will be L1, L2, all the way out to some inductance L sub n over here. Because all of these inductors are connected in series, they should all have the same current flowing through them, some I of t, and they should have some total voltage drop across them, V of t, and we're going to write the individual voltages as V1, V2, and V sub n, like so. So that we can say V is equal to V1 plus V2 all the way out to V sub n, right? So that's just Kirchhoff's voltage law. The voltage rise is equal to the sum of the voltage drops across all of the inductors connected in series. We can express all of these inductor voltages in terms of our current. So the voltage drop across inductor 1 is just going to look like L1 di by dt. The voltage drop across inductor 2 is L2 di by dt, and so forth. So when we get to inductor n, we're going to have L sub n di by dt. And since the current I is the same for all of these inductors, that means that the di by dt term is a common factor. So we'll have L1 plus L2 all the way out to L sub n times di by dt, or LEQ di by dt. So effectively, when we have inductors in series, we can simply add them together, just like we did with resistors. So you're not big on all of this math stuff here. We can just say that inductors in series combine like resistors in series. Anybody have any questions about that?
Not here.
Alrighty, so would you guys care to venture a guess as to how inductors in parallel combine?
Is it the same as resistors?
Yes, exactly right. Do you want me to mathematically derive it, or are we good with just saying inductors in parallel combine like resistors in parallel?
I mean, are there any special cases or is there
Nope.
anything? Okay, so it's exactly the same?
Yep.
I'm comfortable with continuing.
Okay. So I'll just write that here.
But I see there are other students here, and if y'all want to speak, just speak up.
I have a feeling they're sick of me trying to do calculus. All right, so this is where our lecture officially stops. I've covered everything that I want to cover. What I'm going to do now is I'm going to pull up the web work. I want to take a look at a couple of things and make sure that we're all kind of on the same page, and I might help you guys with a problem or two here. All right. So this is homework set number 11, if memory serves me correctly. So this problem right here, I want to start by saying it looks terrible, but if you notice, all of the voltage sources are given as DC quantities, which means this is a DC circuit. So for this particular problem, you should just treat every single one of those inductors like a short circuit, and then this is nothing more than a nodal or mesh problem that you've been doing for a couple of weeks at this point. So the values of the inductors literally do not matter at all. Because this is a DC circuit, simply treat every inductance like a short circuit and move on with your life. So this one looks scary, but really isn't anything remotely new. This problem here is a graph related problem. Obviously there's a big graph on it. You should expect to see a problem similar to this on your exam. I believe there's something similar to this on the in-class assignment. If there isn't one similar to this on this in-class assignment, there's one similar to this on the in-class assignment for the capacitor lecture. So here, you're asked to find the voltage the instant before 6.7 microseconds, or the voltage when you're approaching 6.7 from the left. That's going to be nothing more than the slope. So 13.5 milliamps divided by 6.7 microseconds times 34 microhenries gives you some number. That's the answer for part A. For part B, the voltage the instant after 6.7 microseconds. Well, this is over the time interval where the current has become constant. So the answer to part B should be 0. Part C, it's asking you for the power the instant before 15.4 microseconds. So because the current was constant at the instant before that, the voltage was 0, which means the power should be 0. For part D, Now we have an increasing slope, so we're going to have a positive voltage, multiply the voltage times the current. For parts E and F, it's literally just evaluating the energy expression at those two particular times based on the graph here. So nothing particularly wild or crazy here. Just trying to kind of reinforce that concept of approaching times from the left and times from the right. This is a fairly straightforward problem. Once again, you're just using those four relationships. I give you for parts A and B, you're given L, so you're finding V if you're given I. For part B, you're finding I if you're given V with a particular initial condition, so extremely similar to what we worked. For part C, you're asked to find the power and you're only given I, so you need to be able to take the derivative of it in order to find the voltage, and then simply plug stuff in to get the energy storage one. So that one's pretty straightforward as well. By the way, if you want me to stop and take a look at any of these, I'm happy to do it. Let's see here. Problem 4, this one tends to throw you guys for a little bit of a loop for whatever reason. So let's take a look at this one. So we have a simple circuit here, wherein we have some current source, and our current source is a time varying current source. Then we have a 10 ohm resistor and some number of henries of inductance. It's like 5. And if I'm not mistaken, we're asked to find the voltage drop across the source. So we're trying to find Vn of t, where Is of t is given to us, and we'll just use my numbers here, 2.6 t squared. Amps for t greater than 0. Okay. So before I go into this, does anybody have any thoughts about how we might approach this?
Would we start by taking the derivative of I of S?
So that's definitely going to be part of it, but I'm thinking about, what my end goal here is, right? My ultimate goal is to solve for this voltage Vn, okay? So to me, when I look at this circuit, I see a single loop circuit because all of the elements are connected in series, and that means to me that Kirchhoff's voltage law is going to play some role here. So what I'm going to do is I'm going to call this voltage VR of t, and this voltage VL of t. And if I apply Kirchhoff's voltage law to this system, what I'll find is that Vn is simply VR plus VL. Anybody have any problems with that? Let me make that R look a little bit more like an R, not like a 2.
No, I follow so far. I'm curious how we get V though.
Okay, so how do you think, or what do you think VR is going to be? So let's start there.
Do we need the current first?
What's Ohm's law tell us? Right? So the voltage drop across a resistor is the current flowing through the resistor times the resistor value. So that's just going to be 10 ohms times IS of T. So 10 times 2.6 is going to be 26 T squared volts. Any problems with that?
No, I see now.
Yeah. So, I mean, one of the things that seems to trip students up when we get to this part of the class is they tend to actually overthink things. Ohm's law is Ohm's law. If we know current and we know resistance, we can calculate voltage. Okay. So VL is where we have that derivative-based relationship, right? So it's L dis by dt. So that's going to look like 5 henries, where a henry is a volt second per amp, times the derivative here. So let's see. So we're going to have 2.6 amps per second squared. Just to be really clear here, what I've done is I've said that the units of this coefficient here have to be amps per second squared, because 2.6 some units times time squared has to give us amps. So this is another case where we have to look at kind of the implied units of what's going on in order to figure out how things are going. Now I'm taking the derivative of t squared, which is just going to be 2 times t, where t is measured in seconds. So let me look at things here really quickly. So this amp cancels this amp down here. This second up here cancels one of these here. So I'm left with 5 times 2 is 10 times 2.6 is 26 volts per second times time. Okay. So this is just going to be 26 T volts. And when I add those results together, I wind up getting 26 times T squared plus T volts as the voltage drop across my current source. So we're not doing anything particularly new here other than this derivative-based relationship to help us understand how the inductor behaves. But all of our actual circuit analysis is stuff that we've done before. Kirchhoff's voltage law, Ohm's law, things like that. Just making sure I didn't make any simple math mistakes here. The process is right, even if I did make a simple math mistake, but this looks to be okay-ish. All right, so before we look at the last problem, any questions about this guy?
All good here.
All righty. So we have another problem. Similar kind of situation here. We are given Vs as a time varying function. We're trying to find the current leaving that voltage source. So this is a single node pair circuit because everything is in parallel. So effectively, we're going to do things very similar to the last problem. But instead of writing a KVL equation, we're going to write a KCL equation, right? So let's take a look at this one. So we have VS. I believe we had some resistance here, 10 ohms. Oh, same 10 ohms and 5 henries. That's nice-ish. Oops, that should be a henry, not an ohm. Our goal is to figure out this quantity IN of time. And I believe this is specified to be the inductor current. Yes. So one other piece of information that we're going to wind up needing is this resistor current. And finally, we were told that VS was 21T volts and IL of 0 was 4 amps. So if I apply Kirchhoff's current law to this system, what I'll find is that my current IN is just my resistor current plus my inductor current. So let's find both of these parts individually. So what should IR of T be?
I'm not sure.
Okay, so all of these elements are in parallel, right?
Yes.
Okay. So what's the voltage drop across the 10 ohm resistor?
I do not know.
Well, if they're all in parallel and there's a voltage source right here, then I would argue that the voltage drop across the 10 ohm resistor is just the voltage being supplied by the source. So our resistor current is just going to be Vs divided by 10 ohms. So 21 divided by 10 is going to look like 2.1 T amps. For our inductor current, that's where we have that 1 over L times the integral from T naught to T of, in this case, it'll be Vs of T prime dt prime plus IL at T naught relationship that we came up with today. So that's going to look like 1 over 5 henries. So let's see. So it's going to be 1 amp over 5 volt seconds. I'm going to be integrating from 0 to T of 21 volts per second. So these are some of those implied units again. T prime dt prime plus 4 amps. So when I pull that 21 out, see what's going to happen here. So the volt is going to cancel and we're going to have amps per second squared. What's the integral of t with respect to time? So I pulled the 21 out. What I'm asking for is what is this?
Undefined. I don't see a T anywhere other than where you wrote it just now.
So when I pull the 21, how do I take the integral of t with respect to t? I might be asking
Oh.
the question poorly.
Oh, what, just 1 over T?
1/2 t squared, right?
Yeah. Yeah, hey, you add 1, yes.
So this will be 1/2 t prime squared evaluated at t and 0 plus 4 amps. So let's see, 21 over 5, oh, actually 21 over 10 is going to be 2.1. And then I'm going to have t squared. Let's see, amps, so that's 2.1 amps per second squared times time squared is just going to give me amps plus 4 amps. So when I add all this stuff together, I'm going to have 2.1 t squared plus 2.1 t plus 4 amps is what my current IN looks like. Okay. All right, so I gave you guys some strong help on these last 2 problems. Obviously, it'll be slightly different for you all because you're going to be dealing with different values for VS of t for this problem and IS of t for the previous problem, but the process should be effectively the same. I'm going to leave problems 1 through 3 up to you guys so that you can practice utilizing the 4 relationships that we discussed. If you have any questions, I will hang out here on Zoom until class is over. So let me know if you need anything.
Thank you, Dr. Hartman. Have a good day.
You too, Sean.
Thank you, take care.
You too, Christopher.